Hi everyone, and welcome to my video. Today I am going to present a puzzle problem that was actually a variation of a puzzle problem that appeared over 100 years ago. And we've modified this to just a little bit. And the purpose of this is to show you how a reasonably seemingly simple puzzle like this can really lead to development of advanced mathematics, in particular number theory. So the puzzle goes like this. The houses on my street are numbered 1, 2, 3, and so on. The sum of the addresses of the houses before mine is one more than twice the sum of the addresses of the houses that come after. There are more than 500 houses on my street and less than 1,000. What's my address? As I said, this is a variation of a problem that appeared in a British magazine or a British journal in 1914. And in the original version, the sum of the houses before, some of the addresses before, and the sum of the addresses after are equal. And one of the reasons that puzzle is famous is because it was solved by one of the great mathematicians, Ramanujan, who did this using a continued fraction, and so on. Let's see how this how we tackle this, and we're going to see that we're going to use some of the same concepts that Ramanujan used. So just to give a visualization of this, here are the houses on the street, and here's my house. And as the puzzle said, they're numbered 1, 2, and minus 1. So the first house has address 1, and so on. And to give some little clarity to this, we're going to assign some variables. We'll say that whatever my address is, we'll call that n. So we'll say that my house is the nth house. And we'll say that there's capital N houses on my street. Now, we want to write this into an equation, or a series of equations involving little n and big N. And to do this, one way to do this, we're going to introduce some more terms, because what we're really interested in is this what we call the left sum, that is the sum of all the addresses before my house, and the right sum of all the addresses that come after my house, or to the right of my house. So we can define L to be the left sum and R to be the right sum. And then obviously L plus little n plus R is the sum of all the addresses of the houses on my street. So that's 1 plus 2 plus capital N. Now the problem, or the puzzle, says that L, the left sum, is going to be one more than twice the right sum. So we have this equation, L equals 2R plus 1. So given this, what's the possible values of little n and big N? So we're going to do that just to show you that this does have some. So if we remove the restriction on the size of little n and big N, we could get a solution rather quickly. And in fact, if we only have 7 houses on the street, if we add up the first 5 numbers, 1 plus 2 plus 3 plus 4 plus 5, we can see that sum is 15. And if we skip house number 6 and we just look at 7, well, obviously that sum is 7. This is a case where L equals 15 and R equals 7. And sure enough, that 15 is 2 times 7 plus 1. Okay. So there is a solution. There's also an even sort of a vacuous or degenerate solution, if we just have two houses on the street, we can say that 2 would be a possible solution as well, because in this case L is 1 and R is 0, right? There's no houses on the right, so R is 0. And again, 1 will be 2 times 0 plus 1. Okay. So in this example, we got a case where we got a solution where capital N is 7 and little n is 6. And in this case, capital N is 2 and little n is also 2. Okay. This is kind of a ridiculous solution, because in general we're going to be interested in the case where my house is not going to be at the very end of the street. Now it turns out you can go through all the streets of lengths from 8 to 100, and you won't find any more cases like this where the left sum is exactly 1 more than twice the right sum. So we are going to see why that is and how to find it. And although I should say that there are actually, if you remove the restrictions on little n and big N, there are actually infinitely many solutions. It's just that we're going to see that the values of little n and big N can be quite large. Before we go on, though, we're going to prove a number of little things in this video. But right now, we want to prove one of the basic facts of number theory and algebra, and the way to calculate the sum of the first m positive integers. For any positive integer m, the sum 1 plus 2 plus 3 plus and so and so on plus m is m times m plus 1 over 2. This is traditionally credited by the great mathematician Friedrich Gauss. The story goes that he proved this when he was in elementary school. His school teacher wanted to give the class a problem to keep them busy, so he had them add up all the numbers from 1 to 100. And Gauss did it very, very quickly by essentially coming up with this formula. Don't know if this is completely true, or if there's a good chance that people might have figured this out before that. But that's the story. So where is the proof goes? Well, this is the way that Gauss proved it. You can take the integers from 1 through m and line them up 2 different ways. One in ascending order and in descending order. So you have these 2 rows. Obviously, if you add up these 2 rows, you get the same result as if you added up all of these columns. Right? If you add up the rows, well, the sum of this row and this row, they're both equal to 1 plus 2 plus 3 plus m. Okay, so if we add these 2 rows, we get 2 times this sum. But if you add up the columns, you'll see that the sum of each column is m plus 1. Right? This is 1 plus m is m plus 1. 2 plus m minus 1 is m plus 1, and so on. And there are m columns, so if you add up all the columns, you get basically m plus 1 added to itself m times. In other words, you get m times m plus 1. So you have 2 times the sum that we're looking for equals m times m plus 1. Then we can divide both sides by 2, and we get this sum is indeed m times m plus 1 divided by 2. Now, we notice that we don't have to worry about getting a fraction. This is always going to be an integer, because either m or m plus 1 will always be, either m or m plus 1 will be even. Okay, so keeping that in mind, how do we solve this? So we're trying to find what little n and big N is, given that L is 2r plus 1, and L plus little n plus r is capital N times capital M plus 1 over 2. We can say that now, because that in fact this is the sum from 1 plus 2 dot 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 plus n. And then we also have the restriction that n is between 500 and 1,000. So, there's one other thing we haven't used. We know that L of course is 1 plus 2 plus 3 plus little n minus 1. Okay, now this is the sum of the first n minus 1 integers, so we know that is going to be, basically we're just replacing m with n minus 1, so this is going to be n minus 1 times n over 2. Okay, or if we want to rewrite this in another form, we can write it like that. We also know that we can write r in terms of L. We can take this equation and divide everything by 1/2 and get 1/2 L equals r plus 1/2. So r is going to be 1/2 L minus 1/2. Okay, and then we can substitute that back in here and write everything in terms of little n, right? Because L plus little n plus r is now going to be, this is going to be L plus n plus 1/2 L minus 1/2, or 3/2 L plus little n minus 1/2. So we can set this equal to this now. And furthermore, we can replace L with n times n minus 1 over 2. Okay, now what we're going to do, now we've eliminated all the letters except capital N and little n, which we're trying to solve. We're going to multiply something. We like to clear out the denominators, but we like to do something a little more, so I'm going to multiply by everything by 8. And then what we'll have is this will become 6n minus 1 plus 8n minus 4 equals 4n n plus 1. Which this will be 6n squared minus 6n plus 8n minus 4 equals 4 capital N squared plus 4 capital N. Obviously, we can say 6 minus 6n plus 8n is 2n. And now we can go about completing the square on both sides. We can first factor out this 6, and this becomes n squared minus 1/3 n. And I'm going to leave the 4 over here. And then over here, I'm going to add 1 and subtract 1. By completing this, 4 divided by 2, or rather, because 1/2 4 is, 1/2 4 is 2, 2 squared is 4. So we actually factor out 4. I think you can figure this out why this works, because this now becomes 2n plus 1 squared minus 1. And this, we're going to add and subtract something. We'd like to complete the square here. So this is 1/3 times 1/2, that's 1/6. 1/6 squared is 1/36. So we're adding, we're not really adding 1 over 36, we're adding 6 over 36, or just 1/6. So we also have to subtract 1/6 as well. And now we have negative 1/6 plus 6 times n minus 1/6 squared minus 4 equals 2n plus 1 squared minus 1. Okay. Now we can add 4 and add 1/6 to both sides. So this will be 2n plus 1 squared. Add 4, so this will be plus 3. And then plus 1/6. And then I'm going to multiply everything by 6 again. Now this will be 6 squared times n minus 1/6 squared equals 6 times 2n plus 1 squared plus 18 plus 1, this is plus 19. And then, of course, we're squaring 6, and we're squaring n minus 1/6. And, oops, I think we should make this positive everything here. Sorry about that. And so now this becomes, we can finally rewrite this as 6n plus 1 squared. We can take this over to the other side, minus 6 times 2n plus 1 squared equals 19. And this is, so basically we are solving a puzzle boils down to solving this equation, finding a little n and a capital N in which this is true. And this is going to be a very special sort of equation, which we will discuss in the next part.